All right, so previously we were on the topic of hydrogen spectrum, and let's just sum up a little bit of what we know at this point. Okay, now for hydrogen spectrum, okay, this is where when the electron in hydrogen atoms, okay, jumping from a higher excited energy level to a lower energy level, okay, and the extra energy released during that process because it's jumping to a lower energy level, okay, will be released in the form of a photon, okay. Each of the photon, its energy now, so these are the energy levels, okay, n equal to 1, 2, 3, 4, 5, and when an electron jumps from a higher energy level to a lower energy level, the extra energy is released in the form of a photon. Okay, the photon's wavelengths can be calculated through the Rydberg equation if we know the number of these different energy levels. Okay, and therefore, now there are only certain photons will be emitted by the electron in hydrogen atom, and that's why hydrogen spectrum is a line spectrum. Okay, now this is a specific frequency and wavelengths. Okay, if it jumps from here to here, now that's going to be another specific wavelengths and frequency. And each of them represents a line within the hydrogen spectrum. So you have lots of lines, okay, and that's how hydrogen spectrum is. That's how this works. Okay, now, of course, hydrogen is the simplest atom out there in all elements. One electron. Okay, now, and we have atoms, the majority of the atoms we deal with in Chem 115, okay, have dozens or sometimes over 100 of electrons. Okay, now that one electron of hydrogen can be on all these different energy levels. What about, let's say, an element that has 30 electrons? Where are the energy levels? How did these electrons behave in an energy level kind of scheme? Okay, and that's the thing that we're going to discuss here. All right, so for hydrogen, it's 1, 2, 3, 4, 5, and you see me shrink the energy difference between energy levels going from bottom to top, okay? And if you look back on last lecture's notes with the EM value, okay, equals to a certain number times a z square over n square. Now, you will see as your n goes bigger, okay, your energy level, the higher energy level, okay, the value-wise, okay, it's becoming closer and closer to the previous level. Okay, so that's how it works, and this is hydrogen spectrum. Now, and you can imagine, as you go to elements containing more electrons, the scheme is probably going to go more complicated just to accommodate all those electrons. Okay, so here's what people start to find out. In elements with higher numbers of electrons, okay, this is again n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, and the list can go on and on, okay? And what people have found out is that first, the ground state, okay, remains the ground state, okay? Starting from the second state, second energy level, there's actually some little difference for atoms with more electrons. And that is, well, your n equal to 2 energy state seems like it actually has some kind of a split, okay? It becomes two different energy levels. Go very close to each other, but one a little higher and one a little lower. Okay, now, n equal to 3 also splits, but it splits into 3 separate individual energy states. N equal to 4, 1, 2, 3, 4 different energy levels. Okay, and n equal to 5 split into 5 individual energy levels, so on and so forth. The higher you go, okay, the more complicated, the more splits you would have for a given energy level. Okay, and that's not the end of it. Actually, the more we study about these other atoms with more electrons and with how their electrons behave, we now found out, okay, that again, the ground level is the ground level, okay? The ground state is the ground state, nothing changed to it. The bottom one, the bottom level of each n level, okay, remains the same. The next level actually has some split. And of course, you're wondering, well, you're talking about energy levels, such an abstract thing. What do you mean? Three breaking down into 3 different. They're the same energy, right? Yes, they are the same energy. Okay, but what people found is like electrons that on this energy level, okay, all have the same energy, but they have slight behavior difference. Now, in other words, imagine this. They all have the same energy, but they are actually existing, these electrons are existing in different regions around your nucleus. Okay? Now, there would be 3 different regions for this particular energy level. Okay, we're going to talk about more details about it later on, I promise. I know it sounds confusing right now, but bear with me. Okay, and then for the third level, remember it split into, it went into 3 splits. Okay, now the bottom one, again, nothing happened to it. The next level, same thing. Break into 3 individual, what do we call orbitals? Okay, the third level in that third energy level, that break down into 3 parts. Okay. Actually, the third one have even more splits. 1, 2, 3, 4, 5. Okay. So for the same energy, you can the electrons in at this energy can actually have 5 different behaviors, or be found out in 5 different regions around the nucleus. Okay, and then when you go to n equal to 4, the bottom one again didn't change. The second one break down into 3. You are at this point expecting this. The third one split into 5. And remember, n equal to 4 has 1, 2, 3, 4 splits. Okay, so 1, 2, 3. What about the 4 splits? 1, 2, 3, 4, 5, 6, 7 splits. Now, what about the higher ones? Same deal. Okay, number 5 would have 5 different energy levels. And then those 5 energy levels would be having, from the bottom to the top, 1 no split, okay, 3 split behavior or region, 5, 7, and of course then 9. Okay, the next one would be 1, 3, 5, 7, 9, 11. So on and so forth. Okay, so eventually it's ended in a scheme, much more complicated scheme, like this. Okay, and now we have a dilemma. How do I describe now? Electrons are going off a given atom is going to be distributed into all these different energy levels, different splits. Okay. How do we describe this? Okay. What are each of these individual dashes that we say is a different behavior of electron or different region of electrons surrounding the nucleus? Like, how do you call this? Each individual dash here, okay, whether it's something on top or it's something on the bottom, no, each individual dash is called a orbital, okay? And you can understand it as this is a particular way that electrons can get, who got to that energy, who got into that region, okay, has a special way, okay, of surrounding the nucleus. Okay, so it's called a orbital. It's like satellite circling around Earth. Okay, now, but of course, you see, when we have simple energy levels like in the hydrogen spectrum, we can use one number to describe it. Okay, we can just say n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, and say, well, this is the first energy level, second energy level, third energy level, so on and so forth. But now, looking at our complicated scheme, can you still call this? Can you still just use one set of number to describe this? Where's 1? Well, okay, you're successful here. This is n equal to 1, okay? And then, of course, the 2 levels here are n equal to 2. The 3 levels here are n equal to 3. The 4 levels here are n equal to 4, so on and so forth. But aside from n equal to 1, think about it, n equal to 2. How many orbitals you have? You have 1 lower energy orbitals and you have 3 higher energy orbitals, right? Where is your electron? How do you put your electrons on there? And if, let's say, you put an electron on there, on one of the orbitals, okay, let's say you put a electron here, then you can't just say this electron is at the second energy level, okay? Because again, this is science. Your description is not very clear. Electron is on the second energy level. Well, second energy level have two different splits. If you don't tell me which split is on, I can't even get an accurate energy value for where this electron is at. Okay? And then even if you tell me that, okay, there's a split, this is on the higher split, higher energy split, that still doesn't tell me, well, which one of the three orbitals on that at that energy level your electron is actually at. Okay? So one set of number is not enough to describe electron distribution. And that's why we start to use more sets of numbers. Okay? Here are, and because these numbers are used to quantify, remember we said that the energy level within a given atom, okay, for its electron is quantized, okay, and these new number sets, okay, that we use to describe exactly where my electrons are, okay, we call them quantum numbers. Okay, and there are altogether now four sets of quantum numbers that we use to describe electrons within a given atom. Okay, quantum number one, the first quantum number, of course, is the n that we defined earlier. N equal to 1, n equal to 2, 3, 4. It starts with 1, and this can go all the way up to infinity. Okay? This is what we call the principal quantum number. Okay? And there kind of is also a common name for it. We also call it the shell number. Why do we call it the shell number? We'll explain in a bit. Okay, but this is the principal quantum number. And principal quantum number describe your electrons in, well, where, in general, this electron is being. If you have n equal to 2, you definitely know that it's going to be in these four orbitals at n equal to 2. Okay? So on and so forth. But now, the second set of number that we created is going to help us to differentiate all these different splits within the levels that's separated by the principal quantum number, okay? And if you have, now, and we're gonna say, we use L, okay, to describe, okay, the splits within each n, okay? Or we can say, the reason we use the shell number is that we call this first shell of electron. Okay, this here we call it second shell. Okay, and all the orbitals within n equal to 3 is called, collectively, is called the third shell. All of these fourth shell. So that's why n is also called the shell number. But within each shell, all these splits, now we're going to use L to represent it. And L, which starts from 0, 1, 2, and eventually get to n minus 1. What does this mean? The L value is limited by the m value, okay? And this L here, we call it angular momentum quantum number. Or in other words, we can call it subshell number. Okay? So each, let's say, still using this picture, each shell has a different amount of splits into subshells. Okay? First shell has one subshell. Second shell has two subshell. So one subshell. Second shell has two subshell. Third shell has three subshell. And this, of course, can go on and on. Okay? And this number is also called secondary quantum number. Of course, this is the second one that we discussed. Okay? Yeah. And now, so why are you, if you have 1, 2, 3, 4, why are you using these? Well, think about it. When your n equal to 1, what does L equal to? L equal to 0 all the way up to n minus 1. N equal to 1, n minus 1 is 0. What does that mean? In your first shell, okay, you only have one subshell, okay, that has L equal to 0. Now, as you go to the second shell, though, you would have more L values. What do you mean? Well, think about it. Starts from 0 all the way up to n minus 1. N is 2, n minus 1 is 1, so 0 and 1. Two different values. Okay, and what does that mean? Well, see, these two individual values each represent one subshell within second shell. So this is L equal to 0, this is L equal to 1. What about n equal to 3? Your L should equal to 0, 1, and 2, which is n minus 1. What does that mean? In the third shell, you would have 3 different subshell values. That means you have 3 subshells. So this is L equal to 0, 1, 2. Now you know how to deal with shell number 4 at this point. If n equal to 4, what does L equal to? 0, 1, 2, what's n minus 1? 4 minus 1 is 3, the last number in your series. Okay, so what does that mean? That means the first split in first subshell in your fourth shell is L equal to 0. The second one is L equal to 1. The next one is L equal to 2. And the last one is L equal to 3. Each represent a subshell of the fourth shell. And of course, n number can go on, and the values of your L is more and more. Okay, from one value, two values, three values, and four different values. Okay, each different value represents one subshell. And now, for each of the L value, the secondary quantum number value, 0, 1, 2, 3, 4, 5, 6, 7, 8, whatever. Okay. Now you should realize something here. Okay. Each subshell within the shell always starts from 0. And as you go up in the shells, okay, the shell with the higher number will have more subshells. And this go on and on. And each of the bottom one, see this? Each of the lowest subshell in a given shell have L equal to 0. Okay? And then what people found out is, like, if they're in the bottom shell of this different bottom subshell of all the different shells, okay, if electrons are in there, their behavior and their range of popping up, of being people being able to observe, is actually very, very similar behavior to each other. Okay, and that's where people decided, okay, like n is a number, now it's all these split orbitals and different shells, different splits. I don't want to deal with another set of number. Instead, I'm going to put some letter on these secondary quantum number. Okay, if your L equal to 0, we say this is the S subshell. So the bottom subshell of each shell, okay, the lowest energy subshell of each shell can be labeled as S. Okay, and then if your L equal to 1, which is the 3 split subshell in each of the shells, and we call it p orbital. Okay, and then L equal to 2, we call it the d orbital. All right, and then L equal to 3, we call it f orbital. Okay, and L equal to 4, we call it the g orbital. Now, what about L equal to 5, 6, 7, 8? Do you have more letters for it? Well, right now at this point, I don't need them. Okay, you're gonna find out how we are not needing like more subshell letters. Okay, yeah. And all right, so I was dealing with number, you turned it into letters. What good does this do for me? Okay, well, here's the benefit. Okay, if you combine shell number plus subshell letter, you get something that we call orbital designation. Okay, now, what do you mean? Orbital designation. Well, let me show you. So this is your, let me get a little bit more space. This is your n equal to 1, n equal to 2, n equal to 3, okay, and how do you get this orbital designation? We say this obviously is the first shell, okay, and this is the only subshell of for first shell because you have no other possibilities. Now, and L equal to 0, and but if it's L, we call it a p orbital. If L equal to 0, we call it an s orbital. So this is putting together the number and the letter. We call it the 1s orbital. Okay, and then this one here obviously is 2s. Okay, because this is n equal to 1, L equal to 0. This is n equal to 2, L equal to 0, L equal to 1. Each number represents one of the subshells. Okay, and this is also called 2s because it's the n equal to 2, L equal to 0, and this would be called 2p because it's second shell and your L equal to 1, okay, designation is referring to the p orbital. And then of course the rest of them you can just start to use all these different letters. You can say this is 3s, 3p, 3d, 4s, 4p, 4d, and 4f. All right, and this list go on and on. The fifth shell you would have 5s, 5p, 5d, 5f, and 5g. So once you determine that, okay, you go, well, what about these splits within the same orbital designation, the same subshell? You just told us they're supposed to be different places for my electrons to stay in, okay? How do we differentiate them? Here's where we're gonna need the third quantum number. We call it the magnetic quantum number. Okay, and we use lowercase m sub l to represent it. Why m sub l? Because, well, just like L is limited by n, okay, ML is greatly limited by L. How is this magnetic quantum number defined? Okay, magnetic quantum number, okay, is from starting from negative L negative L plus 1, and because this is the negative value, okay, all the way up to 0, one, two, three, four, then all the way up to positive L. Okay, this is how the magnetic quantum number is defined. Yeah. And now, what good does this do? Remember, we were saying we cannot differentiate, okay, the splits of orbital of subshell, okay, into individual orbitals, okay, and each set we say, well, for example, these three orbitals, you can say there are three degenerate orbitals in 2p. Okay, and similarly, you can say there are 5 degenerate orbitals in 3D. There are also 5 degenerate orbitals in 4D, but there are 7 degenerate orbitals in 4F. Okay, all right, so I know I have more and more degenerate orbitals within a shell when we go higher on subshell, but what does that have to do with the magnetic quantum number? Oh, let's see. What if your L equal to 0? S orbital, right? Okay. ML should equal to, well, what's negative L? Negative 0. What's positive L? Positive 0. Oh. ML should equal to 0. Okay, no other possibilities. All right? Yeah. And how does that reflect on the orbital scheme that we've drawn here? Now, this is S orbital, right? So each ML having only one value means each S orbital or S shell, S subshell contains only one degenerate orbitals. What about L equal to 1 for your p orbital? What does ML equal to? Based on the definition, so negative L equal to 1, so starting from negative 1, and then go up. Well, negative 1 plus 1 is actually 0, so you already got to 0. Okay, and then you would go to positive 1. See that? When you have L equal to 1 in a p orbital, your ML, your magnetic quantum number, will have 3 different values. Guess what's with all the p orbitals? Every single one of them has 3 degenerate orbitals. Okay, so now I can label these degenerate orbitals and go, well, this is negative 1, this is 0, this is positive 1. Okay, each value represents a different set of behavior or a different region for your electrons to reside in within an atom. Okay, now, and what about L equal to 2? For your d orbital, what do we see? We see our ML equal to negative 2, negative 1, 0, plus 1, plus 2. Guess what? All the d orbitals has 5 splits. 3D have 5 degenerate orbitals. 4D have 5 degenerate orbitals. If you have 5D, 6D, 7D, okay, they would all have 5 degenerate orbitals. And labeling those degenerate orbitals now is going to be real simple with the magnetic quantum number. Okay, d orbital has 5 magnetic quantum number. Each one represent 1 degenerate orbital. So you can say this is negative 2, negative 1, 0, plus 1, plus 2. Each of the ML value is representing one of the degenerate orbitals in a subshell. Okay, now seems like 3 quantum numbers is enough to describe every orbital within the scheme that we established. Okay, so if your L equal to 3, you would have F orbital, your ML would go from -3 all the way to +3, and that would give me 7 degenerate orbitals. So -3, -2, -1, 0, +1, +2, +3 for your F orbitals. Okay, so are we done with these quantum numbers? No. Each one is related to the previous one. Okay, L is limited by the M value. Now ML is limited by the L value. Okay, is there another quantum number? And if we do, remember, using these 3 quantum numbers, N, L, and ML, you can pinpoint every single orbital within the scheme that we have. If you cover all the orbitals, shouldn't you be done here? No, not necessarily. Okay, we actually have a 4th quantum number. Okay, and we call it the spin quantum number. Okay, and is the spin quantum number, so MS, is the spin quantum number then limited by the ML value, like ML is limited by L, like L is limited by N? The answer to that question is actually no. Okay, spin quantum number has only 2 positive values. It's either +1/2 or it's -1/2. Okay. Now, why do you need a spin quantum number then? Okay. If the first 3 described, okay, each orbital, each individual orbital, then what do I need MS for? So now let's introduce a little bit of background for you to better understand this. Majority of the time, okay, each orbital can take up to 2 electrons. Okay, they could accommodate 2 electrons. Does that mean that they're? Does that mean they're? How do I say this? Does that mean that each orbital would always have 2 electrons on it? No. Okay, what I'm saying is that each orbital, okay, can take up to 2 electrons. So that means it could take 0 electron, could be completely empty. It could take 1 electron, or majority of times it's going to be taking 2 electrons. But once you put 2 electrons in the same orbital, okay, remember we use those 3 earlier quantum numbers to identify every individual orbital. Okay, so if you look at this one, you go, okay, I'm looking at something in the 4th shell, okay, and then within the 4th shell, also, so n equal to 4. Within the fourth shell, you know, it's subshell. Okay, we know it's in the highest subshell. Okay, L equal to 3 for this case. L, since it's n is 4, L should go up to n minus 1, 4 minus 1 is, no, L equal to 3. Okay, now, and then we also know ML here, we just labeled it, equal to plus 3. Okay, so those 3 sets of quantum numbers really describe every single orbital that's available in the scheme. But when you put electrons into these orbitals, especially when you put 2 electrons into these orbitals, then I gotta be able to differentiate these 2 electrons. How do I differentiate these 2 electrons? Well, this is why MS has only 2 values, because you have a maximum of 2 electrons. So even if you have 2 electrons being put in the same orbital, using the entire set of 4 quantum numbers, you should be able to describe and differentiate, okay, every electron that was put into our scheme. Okay, now, each orbital can take up to 2 electrons using, so we're using four quantum numbers to describe each electron. Okay, and now, and once we establish this, now, one conclusion that we can draw here. I don't know why this is not moving. Okay. Now, no 2 electrons in the same atom would have the same 4 quantum numbers. Okay, now this at this point is just logic. Now, if they're not in the same shell, they would have different m value. If they are in the same shell but different subshell, they would have different L value. If they are in the same shell and subshell, okay, then they could have different ML value if they're on different degenerate orbitals. Okay? And if, let's say, the 2 electrons happen to be in the same degenerate orbitals, that means they have the same M value, L value, and ML value. Well, this is where the MS kick in. If you have 2 electrons on the same orbital, they should have one of each should have one of the ms value. So even if you have two electrons within the same shell, subshell, and orbital, okay, you can still differentiate them by the positive 1/2 and negative 1/2 ms value. Yeah. We'll pick up from here on the next lecture.